So for the rest of the chapter, we're going to predominantly work with beta dicarbonyl compounds. We're going to see a lot of esters, and we're going to see decarboxylation used a lot as part of an overall synthetic tool. So in this first situation, our starting material is going to be acetoacetic ester, which is this compound here. Now notice we have two different pieces of this compound. We have a ketone and we have an ester. We also have two different alpha hydrogens, but one is much more acidic than the other. So any base that we add in here is going to pull off this hydrogen and not even think about the other one, which is important. So if we add in ethoxide, ethoxide again is a weaker base, but the pKa of this hydrogen is probably around 10 or so. So ethoxide is going to be able to pull it off very easily to get the enolate. It's also important that the base that you're using matches your ester, so that if you have any sort of transesterification occurring, it's not actually a transesterification because you're replacing ethoxy with ethoxy over and over. So there is an equilibrium there of attacking this carbonyl and kicking out ethoxy, replacing it with another one. But anyway, that's a side reaction. The one that we want and the one that's going to push this reaction forward is the formation of the enolate, and then you can add in any sort of alkyl halide to put an R group on that alpha carbon. From there, what you usually see is the addition of aqueous acid or aqueous base, sometimes also paired with heat. Remember that the aqueous acid is going to hydrolyze the ester, and you're going to temporarily have a carboxylic acid, but then you find yourself in this situation where you have an alpha beta substituted carboxylic acid, right? So this is a beta keto acid, and this is going to decarboxylate readily. So that what we end up with is our ketone from our original molecule plus a new R group. So this is considered a method to synthesize methyl ketones because acetoacetic ester has a methyl on that side of the ketone, and then whatever this group ends up being would be the other part. So let's say we wanted to turn acetoacetic ester into 2-heptanone. We have to do a little bit of carbon counting before we start here. We know that in order to do this, we are going to end up decarboxylating this carbon and those oxygens eventually. So these three are going to continue into our product. This carbon is going to be our enolate carbon, and we want to add on these 4 others. So we're going to have to add in some sort of butyl halide. So what we want to do is use a base such as ethoxide to create an enolate. Now we can add in our favorite halogen and make sure that we're adding on 4 carbons, because that's how many we need to get into our product. We're going to end up kicking out the bromine. Make sure that you're counting your carbons. So here's our bond that we just created from the alpha hydrogen. This is carbon number 1, the carbon, oops, I don't know how that happened, the carbon that had the bromine on it. And then we're adding on 2, 3, 4. So we're going to end up with 1, 2, 3, 4, 5, 6, 7 total carbons. Now, all we have to do to get from our current position to our final product is get rid of this ester. So we could do that in one fell swoop by adding in aqueous acid and heat. we are going to hydrolyze our ester, and then it's going to decarboxylate. What if we wanted to create a more complicated one? So in this case, notice we have a whole lot more carbons added on, but we're not going to keep this, right? That's not part of the acetoacetic ester synthesis. So both of these carbon groups that we're adding on are being added on through an SN2 reaction. And they are both 4 carbon segments. So this process is going to look very much like the one that we just went through. We're going to add in ethoxide as our base, and that is going to remove the alpha hydrogen to give us an enolate. So now we have our enolate, and we add in our favorite N-butyl halide. 1, 2, 3, 4. Okay, so that's 1 down. We still need to add on another butyl group though. Fortunately, we have another hydrogen. So we add in ethoxide again, and we create our enolate again. Add in some sort of butyl halide. Okay, so now we have 2 butyl groups, and we still have this ester that we have to get rid of. And again, we can get rid of it in one easy move. I just want you to remember also that when you do this, you are going through the carboxylic acid, and don't forget about that. The heat is what causes the decarboxylation. So why are we using acetoacetic ester if our goal is to make a methyl ketone? Because then we have to go through the whole process of decarboxylation. That just seems like a lot of extra steps, right? You're probably wondering, why not just use acetone? Acetone has an alpha hydrogen that could be removed using LDA or something. We could create this enolate. But what you have to remember is that this hydrogen is much less acidic, right? So you do have to use a stronger base such as LDA in order to get this enolate. But also, we have 2 sides, right? We would not have control in order to make the specific products that we wanted. So doing that dialkylation, like in the synthesis we just looked at, would be nearly impossible because LDA is not going to want to deprotonate here if it can deprotonate here. So we can't do that. So acetone and acetoacetic ester are considered synthetic equivalents because you can get the same type of synthesis done, but using acetoacetic ester is going to be much easier because no matter what, an alpha hydrogen in between the ketone and the ester is always going to be the most acidic. It is always going to be the one that is pulled off by a base. Okay, so we're going to step up our synthesis a little bit here because synthesis is a very large learning goal for organic too. So naturally the problems are going to start getting more complicated. You may notice that in this reaction, we are going from an alpha beta substituted situation to alpha beta gamma. So this is actually considered a gamma keto acid. So the carboxylic acid is going to be the more important thing. So there's a ketone in the gamma position. Somehow we are inserting another carbon between these. Now that's not chemistry that we've learned, so that's probably not what's happening here, right? This is acetoacetic ester. We know that with this, we can pull off this hydrogen. So the question is there a way that we can use this alpha carbon to add on this piece? So this is where like a retrosynthetic analysis could be really helpful. You could imagine that before this, we may still have had the ester on and it was decarboxylated, right? And that would be very clear that the carboxylic acid was added on through SN2 chemistry. So I could get here by adding in aqueous acid and heat, right? I would end up hydrolyzing and decarboxylating this ester, but these two groups being gamma to each other, this is not going to end up decarboxylating. So that's our process forward, right? So let's add in our ethoxide and we create our enolate. Now somehow I want to add on a carboxylic acid and another carbon. So I guess there must be a leaving group on this carbon. So I'm going to add on a halogen there. Hey, this is an alpha halo acid. Maybe there's, a reason that we learned how to synthesize alpha halo carboxylic acids not too long ago. So that would be a complete synthesis to get from acetoacetic ester to this gamma keto acid.